Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collections as usual. Today actually not really a theorem, but rather kind of an idea which I would like to tell you about, which I knew for quite a long time, but of course I forgot about it. Well, what can you do? And I was recently reminded, I will show that to you in the very end, about whatever, fuzzy logic or fuzzy sets. The original paper is called fuzzy sets. Because I looked up the most cited math papers of all time, and fuzzy sets, apparently, to the study I found, very, very, very hand wavy, of course, is the most cited math paper of all time, which kind of says a little bit, at least a little bit, right? So we all know that mathematics or life in general is not ordered, linearly ordered. So whatever that means, most cited, but it certainly is much better than any of my papers, for example, because it has way more citations. And what is so cute about it, left aside citations, of course, is that the idea is kind of really, really nice, pretty straightforward. It's one of those ideas where you really think, ooh, I could have done that. I could have thought about that. I could have written that paper, which is the hindsight bias, which is, of course, not true. I couldn't have, but at least I have the feeling that I could have, which is already pretty cool. So it's a very nice idea how to kind of bring in probability theory into logic or set theory or whatever. So it should be kind of at the foundation of mathematics. So kind of the slogan here is that everything kind of depends on a probability measure. So this video, for example, is 90% just crap. Of course it is. All my videos are 90% crap, at least 90%. I was thinking whether I should do it 99 or 95, but I think it doesn't matter anymore. You will get the point anyway. So this video is 90% crap, which is a statement I can't do in the classical binary Boolean logic, right? I could only say this video is good or this video is bad. But obviously, there should be some statement like this video is XY% bad or good or whatever, right? And that's where this fuzzy logic or fuzzy sets is where those come into the game. I will mostly stay with fuzzy sets, but kind of fuzzy sets and fuzzy logic are used interchangeably anyway. So let's have a look. It's actually kind of a nice idea. And you really wonder why it took so long to enter mathematics or logic or whatever you want to call it, because it's kind of really straightforward in some sense. Brilliant, obviously. I couldn't have written that paper, as I said, but still straightforward. So kind of Boolean logic is what you can see here at the very top, and kind of fuzzy logic is what you can see here at the bottom. So kind of you start with a question, and we all know that mathematics is then giving you a 0 or 1 answer. Is the water hot? Yes would be a 1, and no would be a 0. And that's kind of the standard Boolean logic, right? In mathematics, or in this part of Boolean logic, and kind of in a lot of cases in the real world as well, we kind of try to approximate everything by saying either it's black or white. It's black or it's white. There's nothing in between. No shades of gray. There's nothing in between. Of course, we all know that is not true in the real world. We all know that life is not black and white, but we like to approximate it by 0 and 1. And mathematics is kind of at the forefront of everything. In mathematics, there's no approximation. It's just yes or no, which is kind of what it makes so interesting, what it makes it so nice, because you get a smoother answer, right? If you kind of ignore all the problems of real life, you tend to get nicer answers. A yes answer is certainly better than a I'm not quite sure answer. So right, we like to hear yes and no, right? As humans, we really like to hear yes or no. And this is kind of what this is all about. In fuzzy logic, well, you just build life into logic if you want. You allow, kind of in my nutshell picture here, a little fuzzy logic in a nutshell, you kind of allow all possible values between 0 and 1. So is the water hot? It could be very much hot, whatever you would give it a 0.9, so 90%. Is it a little bit hot, whatever, 0.25, if it's not really hot, a 0.1, something like that. And we all know that kind of makes way more sense from the viewpoint of life, right? Mathematics is based on Boolean logic. Life is not really based on Boolean logic. As I said, we all know that this is really true. So kind of the idea that started this fuzzy logic, so the kind of the opposite, if you want, it's not really the opposite, but kind of this idea of building life into logic is fuzzy logic, and maybe we should start doing mathematics and logic and whatever kind of as at the root of science. Maybe we should already start doing it using the logic of life, the not yes or no logic, the not black and white logic, but the logic of, well, it could be, it cannot be, it is 0.5%, whatever, true or not. So it's not a yes or no, but it's rather a maybe. It's kind of a maybe logic, just a very fuzzy logic in the sense that you have a lot of possible values that your logic, you have a lot of possible values for hot water, right? It could be 0.5, could be 0.6, anything basically. And that's kind of fun, kind of a fun idea, right? The whole point of mathematics over the centuries, over decades, whatever, was that it is actually so easy that it simplifies everything to a yes or no question. Maybe that's why it took so long. I show you later that this paper isn't all that old in some sense, right? This could have been done by people in the 15th century or even earlier, but it's actually from the mid 90s, 1900s. We'll see in a second. But keep in mind that the question we would like to address here is, how can we kind of build in life into mathematics, right? And sort of mathematics built on life instead of mathematics as something like that is black and white. And here's kind of the idea how to do this. You kind of have a membership function. So you should think of, okay, we have a set, and the set will be enriched with this membership function. There will be a membership function that tells you, for each member, it is a certain percentage in the set. So in this example here, there will be a membership function that assigns a value between 0 and 1 to, let's say, humans. And the question here is whether they're tall or not, whatever, right? It doesn't really matter what kind of question it is. So here you have a not so tall, here you have a tall human in this illustration. And it would associate to each one of those elements. So there will be a set of humans, and it would be associated to each one of those elements a certain value depending on kind of how tall they are, right? So whatever, there's not very tall is 0.3, or it is very tall person 0.95, something like that. So a fuzzy set is actually not just a collection of elements like a classical set, but it's a collection of elements that kind of exists with a certain probability, 0 or 1. And this is this probability function, the membership function, which just assigns to each element of X a probability, namely how much it actually is part of the set, right? If it's just a 0.3, it's kind of a pseudo member. If it's a 0.95, it's basically a member. It's kind of the idea. And you can do a little bit stricter. You can say, if it attends 0, then it's definitely out. If it is 1, then it's definitely in. And everything in between is like this probability. It's partially inside of your set, right? It's kind of cool, right? So you can now think about sets and elements that are partially in your set. And well, this picture here with height makes sense, and this picture here with hot water makes sense. It's kind of pretty cool idea, right? So this fuzzy set is then a set with kind of a probability measure. So this is how I would like to think about the fuzzy set. So the fuzzy set, so classical set is a dashed one, and the fuzzy set here is the blue solid one. And the fuzzy set is really more like a probability function. Some little function here, and all members could be inside or outside with a certain there's a membership function that kind of decides how much they are in or outside. You can think of it like some probability curve here. In this case, it's this one here on your set. And the difference is kind of the classical function only attends, so the classical set is like the probability function that only spits out 0 or 1. So it's actually like this box type function. So classical is this box type function, is 0 for some, and it's 1 for some others. So it's really like a box. While kind of the fuzzy logic, the fuzzy sets are kind of anything you can imagine. It doesn't need to be as smooth or nice as this one. It could be whatever, something like this, or something that I can't even draw. It doesn't really matter. But you could think of it like a box in contrast to kind of any function, right? So fuzzy sets in some sense generalize hugely sets because they are now like box functions, like rectangles compared to any other function. right? So the picture here is the same. So here is my value of mu, and here is kind of the set x. It's not quite right. It's just an approximation of the picture, right? I think you get it. Of course, I can't just think of my set as being one-dimensional. But in this approximation, it works pretty well. So I say it again. What I wanted to say, the set x, the fuzzy set is really more like any function, and the classical set is a special case of a fuzzy set. It's like this box function. The box function just says 0 or 1, and any other function just whatever any other function does. But it can take any value between 0 and 1 in any strange pattern you can imagine. So you can really build this as whatever kind of problem you have in mind. You can find some fuzzy sets that kind of addresses this problem in some kind of mathematical way. It should be something like the foundations of fuzzy type of mathematics. It's not as well developed as it deserves to be. It gets a bit more complicated because it's not a black and white logic anymore. But kind of the theorem here, of course, theorem and huge quotation marks, is this fuzzy set theory works actually pretty well. You can have unions and intersections and so on. You can build kind of the whole theory of sets, set theory on fuzzy. I will explain intersections and unions in a second. But kind of the theorem, as I said, is fuzzy logic works. And in principle, we should be able to build mathematics on fuzzy logic, which is kind of a cool idea. Whether this will ever happen in practice is another question. As I said, the field is not as developed as you would like it to be. Anyway, so let's have a look at the definition. I basically already told you the definition. It's up here. A fuzzy set is really a pair of a set and this probability function, the membership function. The membership function is really like those little boxes here. So here's a membership function. Here's another membership function, right? So this is how I would like to think about those membership functions. As I said, they don't need to be smooth or whatever, but I still like to think about them like this little probability curves, if you want. And the union here has a very nice, and the intersection as well, a very nice geometric interpretation. So the union of this guy here, which is a little bit like this little block here, this little whatever it is, spike, is this picture. So you kind of put them together. As you can see, they're put together here. This one goes here, and this one goes here. And you take the maximum of them. And for the union, you kind of do the opposite. So the union gives you another spike function, and the intersection, I should get rid of this crap here. The intersection also gives you another nice spiky function, or whatever you want to call it. It's like this guy here. So the union is another one of those functions. Intersection is another one of those functions. So union and intersection for those sets make sense because, of course, the idea here is that drawing those pictures is equivalent to the datum of a set and a membership function, right? So kind of the point here, I said again, is you could, or we actually can, make fuzzy logic work in the sense that most theorems of set theory go through. So we could use this as a basis of mathematics. It's kind of a really fun idea. Instead of having a box, it's a 0-1 box. It's really just any function. And you can make sense of, is the water hot or not? Are people tall? Yes or no? Is this video crap? Yes or no? Not just in the yes or no fashion, but in this video is 90% crap fashion, right? That's kind of the whole point. Okay, let me show you why I was reminded about fuzzy sets. So let me just pull up the website, which is, of course, linked in the description. So here's the website, and it was, it's a Nature paper, and they studied the most cited papers of all time. They had a specific metric to do this. We all know, as I said already, this is not linear. So it's kind of a little bit hand-wavy how to order those and how to measure citations anyway, and how important are citations anyway, and all those questions. Let's ignore that. Let's all ignore that, and let's just have a look at the outcome. So what they do is you can have a look at, as I said, as the website yourself. It's freely available. The link is in the description. And they list the 100 most cited papers of all time, whatever, in the metric they use. And how this works is, well, they have this ranking, and the measurement is, of course, how many citations a paper got. So apparently the first ranked paper has by now, or whatever, when it stopped, 2014 or whatever, 2014, It had 300,000 citations, which is ridiculous. 300,000 citations. This is not like subscribing to a YouTube channel, which just takes a second, of course, or subscribing or following on Facebook or whatever. This is really spending 1 year of your life working on this and then citing this paper. So 300,000 citations is a really, really impressive number. It's a really, really impressive number. And well, it's this paper here, apparently. And they order it according to fields. The one we are interested in is this purple here, mathematics and statistics. And as you can see, the first, well, of course, fields are biased. Some fields are bigger than others, so they will appear more likely towards the top. Some fields have fewer researchers working on it, so they will appear more likely towards the bottom or not at all. So this is really a biased perspective. As I said, let's just ignore all of that together and let's just look at the data. Okay, so apparently the first mass paper, well, it should be some purple. It's here. So it's here. You can click on it. It's position 46. It has 18,000 citations. What a ridiculous number. Just think of it like, let's say 2 people cite this paper per citation, because 2 people work together, then it's kind of a double here. 36,000 people have cited this paper, a rough estimate, and everyone spent a year working on this. Oh, this is quite a lot of work here. Oh, I mean, 18,000 citations is ridiculous. Anyway, it's well, the topic of this video. It's fuzzy sets. So fuzzy sets apparently, according to this study, I need to say it again, I have said it very often by now, is apparently the most cited math paper of all time. There are some other math papers here. I think this one should be one, and so on. But as you can see, well, you can click through it. So if you like, whatever, red, and here 36,500 citations. Okay, back to my slides. As I just told you, life is not Boolean. Obviously, life is also not linearly ordered. So take everything I just told you with a grain of salt, with a huge pinch of salt, actually. Anyway, so there is some reason why fuzzy sets, so fuzzy logic, is one of the most cited papers in mathematics. I think mostly because it's such an easy idea. It's really easy, right? It's just a membership function associated to a set that you have the feeling like, I could have done that. That's, as I said, the hindsight bias. So that's certainly not true for me. So I couldn't have done that. But at least I have the feeling for a second that I could, which makes it pretty nice. Yeah, so let's wrap up. So this nice idea of building in life, if you want, into mathematics, fuzzy logic, like a set together with a probability function, if you want, kind of this mixture of probability theory and set theory, which should serve as a nice foundations of mathematics. It isn't as well developed as it deserves to be because it gets a little bit more complicated. But the theorem here was the theorem in huge quotation marks, of course, was the kind of all of classical set theory, whatever that means. Let's just make it a huge quotation marks, kind of works in the fuzzy set sense as well. And I think fuzzy certainly deserves more study because I would like to say this video is 90% crap, and I can do that in fuzzy logic, but I can't do that in Boolean logic. Anyway, I hope you still enjoyed this video, although it's 90% crap, and I hope to see you next time.